So my name is Molly Hall, and I'm presenting an overview of the research that I completed for my PhD here at Center for Future Materials. So this work was completed last year, and I'm going to give an overview of the methods that I used, and I'm really treating this more as a masterclass in how we use dielectric sensors for cure monitoring, specifically thermoset composites. There are potentially some analogous techniques for other material systems, but we're really focusing on epoxy chemistries here. So I'll start with a problem context, sort of explaining why any of this is important, and start with a bit of background on sort of why we would need to use dielectrics in the first place. Part of that is talking about how we currently model thermoset cures and some of the challenges around the modeling practices. And then I'll explain how dielectric analysis works and walk you through some of the methods that I developed through my PhD. So there's a few different techniques that we'll talk about, and I'll end with sort of the more unique aspect of my research, which was investigating a novel sensor type that can actually monitor through the thickness, if you can see my camera, of 2 centimeters or potentially more than 2 centimeters thick of composite cross sections. So for those of you who might not be as familiar with how the aerospace industry does composites, there's a lot of testing and a lot of analysis, a lot of steps in certification to ensure that everything that goes on a plane is exactly what we're expecting it to be. Some of the lower spec applications of composites, so like potentially marine and wind energy, essentially if it looks good, it's probably good. And they might do some testing to validate that, but essentially if the boat comes out and it looks fine, they're assuming it's fine. For aerospace, unfortunately, we can't make those assumptions. So we really start at the beginning with a very lengthy process to certify the materials that are going into these components. So within the material certification and qualification processes, there's a lot of properties which are tested to capture what the ranges of those materials are, what their limitations are, how consistent they are. And then from there, we apply that into our parts and our components and our structures. So each individual part needs to be validated to some degree, and that involves making parts, testing them, and ensuring that that part performance is exactly what we're going to expect it to be. From there, we go into the part production. So once it's verified that that production system is stable, they can continue to make parts that can continue to be put on airplanes. Within part production, we still do a lot of testing and verification to make sure that those parts are compliant to what our requirements are. And the 2 main ways that we accomplish all of this is a combination of actual part testing and materials testing and simulation. Within thermoset composites and thermoset polymers, one of the key components of the simulation is modeling the cure. So within these classes of polymers, we start with a lot of characterization, usually by DSC. There's a few other techniques as well. And we'll then develop a kinetic model. So this model, and here's my crazy equation that I think Hadi volunteered to explain for me. So this is the kinetic model for specifically the material system that I used in my research, which is SciComm 5320-1. This model was proposed by a research group in California, and it seems to be the most accurate one for this epoxy. But that model was developed through a huge amount of testing. And that essentially what this tells us is over specific temperature conditions and time conditions, what is the outcome of the cure that we can expect? So when we're doing these simulations, and I have an example here of how a cure simulation system that I used, which is Convergent Raven. So we essentially have this kinetic model. We have our processing conditions that we're assuming, which are heat and our heat transfer. And we look at what are the outcomes of this cure. So I know there's a lot of things going on this graph. So essentially here, our dark blue line is our temperature profile that we've put in. We have our red line is our resin viscosity. We have our light blue line is our reaction rate. We have our TG, which is, I think, our green line, and our degree of cure, which is that dotted purple line. So there's several things that we can predict for the outcome of this cure. Now, the challenge that we have here is we have one set of inputs that gives us one set of outputs. So we essentially assume this model's perfect. It perfectly captures what's going on in this specific polymer. Our temperature conditions are perfect, and they're exactly what's going to be shown in reality. And that gives us one answer. So from all of those inputs, it tells us this is your degree of cure, and that will always be your degree of cure. Unfortunately, what we know is that there's a lot of variation in the system, and that leads to variation in the outputs. So starting from the beginning with these polymers, there's some variation from polymer. There's a lot of variation from polymer to polymer, but even within one specific chemistry, there's variation between the different batches that, depending on how much exact monomer content you're putting in, how it's processed, you do get some slight variances. There's also variance within the kinetic model itself. So unfortunately, these are not all perfect. There's a lot of variation depending on how you collected your data, who did the analysis, what assumptions were made, and what specific batches were used to develop that model. So from doing a lot of analysis, there's actually a fantastic thesis written several years ago that assessed all of these different variations and figured out that there's about 10% variance that you can expect out of your kinetic model, which I don't want to alarm anyone, but 10% variation on these is quite a lot. We also know that we have very natural variation in our processing conditions. So that's due to just the equipment variability, heat transfer, ambient temperature can be an influence. There's a number of factors here. And we typically consider that our temperature will vary within 5%. That's a pretty standard limitation within aerospace. So all of these variances sort of stack on top of each other, and they give us this unknown variation in our cure outcome. So for the research that I completed in my PhD, I really focused on just the variance from the kinetic model and the processing conditions. I was using one polymer, one batch of one polymer. So for the following slides, we neglected any variation from the actual polymer itself. But yeah, there's a big question of what the variance is, and the approach that I used in my PhD was to develop a stochastic model to capture, based on the variation that we expect from our inputs, what is the expected variation from our outputs. So I have up here a few different output parameters that we looked at that show a probability distribution based on the degree of variation that we looked at. So we looked at a few different extents of variation of these two categories, the cure kinetics and the temperature. And additionally, we looked at those together. So seeing how those two things stacked on top of each other. So just to draw attention to a few things. So for example, time to 88% cured. The significance of this is 88% cured for this polymer is commonly considered what we call fully cured. So it's very uncommon to get to 100% cured, 100% converted in these polymers. We don't usually require it to. We tend to define a threshold for how like at this level we have the extent of properties that we're expecting from it. So the 88% cured, if you're looking at this in the lowest variability case, which is under just a measured temperature variability of 1.5%, which was the variation that we saw on our very small lab oven, we're still seeing a variation of about 210 minutes to about 235 minutes. So that's a 15-minute window with our minimum amount of variation, and that's not insignificant for processing. And this is sort of the issue. So our current minimum cure time for this material is about, with this cure cycle, it's about 275 minutes. So at that point, we're expecting that all of our parts are going to be sufficiently cured, and there's not really a risk there. That's our factor of safety to ensure that all of these components are cured. However, there's always a push to optimize our cure and optimize production time and manufacturing time. And the number that commonly gets thrown around is 30-minute reduction in cure time. So if you look at this, if we're trying to reduce this to 240 minutes, there's this whole section of parts that are at risk of not being fully cured. And that does introduce risk to our process. So the clear solution here is not, oh, we can't optimize, we have to have these long cures. To me, the clear solution is we should monitor them directly so that we know if that cure is actually completed to the point that we need it to. There are several ways of monitoring the cure progression. Thermocouples are probably the most common. If you stick a thermocouple in the middle of the part, you can measure the temperature profile that that specific part is experiencing, pop that into your simulation, and predict how well cured the part is. However, for flyaway aerospace applications, unfortunately, we can't go fly with the thermocouple hanging out of our parts. So we need a technique that's non-invasive. So the technique that I've used and that I'll talk about for the remainder of this presentation is dielectric sensors. There are two main types of dielectric sensors that I'll talk about today. So the most common type is your interdigitated electrode sensors. So I specifically used the NETCH IDEX sensors to start off my research. These are off-the-shelf sensors that you can go buy. They're very well understood. They do tend to get embedded in the part. They can also rest on a surface of the part. But this one we do consider to be a little bit more of an invasive method. They have a very small spacing between the electrodes, and this means that they're really getting a contact measurement of just the surface that they're touching. The other type of sensor, and we'll ignore the through thickness statement there for just a minute, but there are tool-mounted monotrode sensors, which are like the one I'm showing here. They're mounted into the tool, they touch the surface of the part, but commonly these sensors are also only taking a contact measurement. The unique part of the sensor I used in my PhD is that it actually can make a reading through the entire thickness. So based on the design of the sensor, you have the circumferential electrodes that cast an electric field. For this one specifically, it was designed for a 20 millimeter penetration depth. So here's my component that I cured during my PhD. So this is about a 2 centimeter thick chunk of carbon fiber that we used to monitor how this sensor performed. But this one's very unique. The sensor is a prototype, and hopefully we'll start seeing more of these break into the market, because it does give you that huge advantage of being both non-invasive and capturing what's going on through your thick components, which is a big challenge in aerospace. But how does dielectric sensing actually work? There's in your thermoset, so I'll take the fibers out for now. So the fibers don't change through the cure. What happens during curing is your polymer is changing, and that's what we want to capture. So within your polymer, you have dipoles, which are commonly polymer branches or subgroups that are off of your polymer, and you have ions that are kind of floating around. These are commonly either impurities or unreacted monomers. What happens with this sensor? So you have two electrodes. In the previous slide, you see in the interdigitated, they're comb electrodes that are spaced in between each other. In the TMM sensor, we have the circumferential electrodes. What I'm showing here, just for the visual, is actually a parallel plate configuration. So you have one electrode on top, one electrode on the bottom, with your material under test in the middle. And this is not what I used. It's just a common way of representing how they work. So with your electrodes, and in this sensor, you're essentially fluctuating an electric field on and off constantly at there's multiple frequencies that you can set that to. So when your electric field goes on, your dipoles align under the electric field. Your ions also start to move from one electrode to another. But then the electric field goes off and your dipoles relax and your ions stop moving. And essentially keep doing this constantly through cure. As you continue to cure, your material starts to cross-link and it freezes things into place. So your dipoles have a much harder time relaxing and aligning, and eventually they stop moving entirely. And your mobile ions get depleted or they get frozen into place and they can no longer move. So this is really the principle of dielectrics for thermoset monitoring. Is we're seeing how these electric charged particles are getting frozen through the cure, and that's allowing us to monitor what's happening in the cure. So with this monitoring of the dipole and ion motion, we develop a phase shift between the application of that voltage, which causes that electric field, and then the response current, which leads to a material admittance. The material admittance is a ratio of your conductive response and your capacitive response of your material. And from this admittance, there are several different dielectric signals that you can actually use to monitor your process. So we have our dissipation factor, impedance, ion conductivity, permittivity, and loss factor. So 5 different signals all relating to the same behavior that's going on. Now, one of the challenges that I dealt with first in starting my PhD was there's a lot of literature on people who have used dielectrics for thermoset cure monitoring. But essentially, everyone's using their own techniques. They've sort of picked one of these parameters that seemed to give the best results. And there wasn't really much consistency between the methods that were being used. So the first thing that I looked at is, why can't we just use all of these parameters independently? So up here you see our equivalent circuit diagram. This is specifically for the through thickness sensor that I used, and it captures the where the response comes from, depending on where your fibers are, where your resin is, and that interface between your fiber and your resin, and how that all contributes to the signal. So I have a bunch of equations up here, and these are your 5 dielectric parameters that we use. And what I want to highlight is all of these are driven by either your conductance or your capacitance. And because all of these are tied to those 2 parameters, which are tied to your material admittance, the first question is, why can't we use all of these independent, or why can't we use all of these interchangeably? And essentially, we can. So here's from one signal, from one cure, here's all 5 dielectric parameters. And what I've done is overlay the cure events that we know from simulating that specific cure from the temperature reading that we collected. So what you're seeing here is that essentially, so for example, this blue line is our minimum viscosity. All of these parameters sort of have the exact same trend. They hit their peak or their global minima at the same point. They increase at the same point. They end at the same point. So this was a really useful finding, that we can use all of these parameters interchangeably. The next step from that was, how do we use these and how do we tie the dielectric signal to information about what's happening with the cure? So here are the 5 methods for identifying different cure points that we proposed in one of my first papers. So to start with, that initial inflection in your signal, where you see the signal drastically rising, and because of that rapid change in the ion viscosity, that's your onset of your cure reaction. So your material is starting to move a lot and you see that rapid increase. The global maximum or minimum in case of your impedance is the point of minimum viscosity. This is one that has been suggested in literature previously, but we extended that analysis to all 5 parameters with good success. And this one's quite well accepted, that your maximum signal, you have the maximum ion mobility, and that's correlated to the maximum polymer mobility. The next one is the gel point, which I've correlated to that end set after that global maxima or minima. And the reason for this is the way I've defined gel point in this work is the rapid increase in your mechanical viscosity of the material system. There's several ways that others have defined gel point, and maybe some of the other proposed correlation methods that were previously in literature aligned to one of those definitions, but this is the definition that I've used, and it aligned quite well to that rapid slowing of that dielectric signal due to that rapid change in your mechanical viscosity. The vitrification point, which for this I've defined as the crossover of your TG and your temperature, which aligns to that shift to diffusion dominated cure, aligned very well to the tangent point after that end set. So where that signal really starts to level out. So if you notice on this, the signal doesn't get perfectly flat. And this definition is how I've defined vitrification for this. There are several other correlations that have used definitions like when the signal levels out, when the derivative reaches 0, when it plateaus, and these definitions didn't really work for how my signal was showing. So I think generally these probably all intend the same thing, but this is the definition as I've used it. And finally, the end of the Cure reaction, you see the dielectric signal takes a sharp downturn, and what's really happening here is the Cure process is over, and the Cure profile of the oven has ended and the temperature has started to decrease, which is leading to a reduction in the signal. I want to make a clear distinction that we're not defining this as the completion of the Cure reaction. Instead, this is the ending of the Cure reaction because we are no longer putting in sufficient temperature to continue it. So what this really aligns to is when your reaction rate goes to 0. So we're not at fully 100% conversion, we're at the reaction rate has ceased. So aside from our Cure points that we can identify, there are several ways of calculating degree of Cure out of these signals as well. So this is a equation that has been proposed for some of the parameters previously. And again, we've shown that it is also parameter independent, and it can be applied to any of these signals with decent success. So what we do here is we sort of cap the beginning of the equation we're considering at that global maximum, where you have the ion movement is the dominating contributor to your Cure reaction, and then we cap it at the end of the Cure reaction. So when we're stopping that reaction rate. I will also say that this equation, if you ignore this alpha raven, assumes you reach 100% conversion, which we know is not the case. So we do normalize this by either a simulated or a measured degree of Cure. So if you measure degree of Cure using DSC, for example, that can normalize this as well. But I used the Raven simulation to do this. So this technique, as I said, is also parameter independent. We also showed that it is quite repeatable from part to part across different replicates. The word prediction on this slide might be a little bit hopeful, but there's another method for determining the degree of Cure progression that was proposed out of a research group in the UK. And for this technique, they really focused on the impedance only. So again, we were looking at this method for, is it parameter independent? But this technique, they correlated the degree of Cure progression with the dielectric signal and determined that there's a pretty good linear correlation there. And they used that equation to then go predict your degree of Cure over the rest of the range. And this worked quite well for the rest of the parameters. And I say The prediction is in italics, and I say it's a hopeful term because if you can determine that these equations are sort of law for these materials, which we have some indications that they could be, you could theoretically use these equations to predict any degree of cure as the component is curing. So I think this one has some very interesting promise. And then finally, to bring this into the through thickness measurements. So all of these works were done on the IDEX sensors, so in plane sensors, which are quite well understood. We then extended all of these techniques to the concept of through thickness dielectric sensing. So again, the maximum was this 2 centimeter thick, I think it's 144 plies of carbon fiber. But we looked at several different thicknesses down to 2 millimeters and showed that these same techniques can apply quite well to all of these thicknesses. Again, they're all parameter independent and they're quite repeatable across different part replicates. So that was a really good success. I will note that this sensor, because it's a prototype, we did need to add a correction factor, which accounts for the sensor design, temperature compensation, and thickness. But once we applied that, we had very good correlation with all of our properties, all of them being within 5% of what we predicted from our simulation, which is quite close. And yeah, worked out quite well for also for both the cure point and the graphical methods as well. So just to conclude, composite processing happens under uncertainty, and it's always good to capture what that uncertainty is. If you can't, then directly monitoring your cure process is really the best way of going. And dielectrics, I think, are a very effective solution for this, especially for aerospace, because there are some non-invasive solutions. And that's what I have. Thank you for listening, and I'm happy to. If anyone has any questions, you're welcome to put them in chat or come off